Hello and welcome. Introduction. Now in this video, I'm going to show you how to control an LED on the Tiva C series LaunchPad board using the TM4C123G UART module. So the main objective of the program is that when you press the number 1 key on the keyboard, then the LED, the green LED, should turn on. And when you press the 0 key, the LED should go off. And that is the main objective of the program. The program complete listing. So here is the complete listing of the program, and let's start off with this section here. Here is the initialization section, and then followed by the declaration of the registers that are used in the program. And I won't go into the details of all these here. In fact, if you want more details of these registers, please refer to my previous videos, and I have included the links to those videos in the description. All right, so viewers that are new to the channel, and if you want to know more, please refer to those videos. Anyway, let's come back to this. So here is the beginning of the main prop routine. All right, it stretches all the way to this point here where it says ENDP. That's the end of the routine. Now, very quickly here, what we have here is these 4 instructions here. Basically, they BL, for example, BL enable clocks will actually call this subroutine. All right, so these are the subroutine. This enable clocks that will enable the clocks. Then this initialize port F and initialize UART 5 module config UART 5 module. So these are basically subroutines, and they are being used in my previous video. Again, I refer you to my previous videos for the details of this. So let's move on. Now here we have we're setting up register R4 with the base address of a character table. Now the character table, if I just quickly scroll down, here is the character table. All right, with the message, and the message is press 1 for LED on, 0 for LED off. So this is the character table, char table. Let's move back up here. Right, so this will set up register R4 with the base address of the character table, and then here we'll set up the counter using R5, register R5 as the counter, and we clear the register, initialize the register to 0. Okay, so from here, the loop to this portion of the code here, where it says branch B for branch to loop. Now this few instructions here, basically, especially this one here, BL UART 5 transmit, that would display the message that we have seen earlier in the chart table, and here the BEQ scan input. This was then scanned for the input, which brings me to this part. This part here, basically, this part here will look for the numeric 1 key and the numeric 0 key. So this portion of the code here will look for those two keys. Now, if the numeric 1 key is pressed, then the green LED will come on. Now, if the 0 key is pressed, then the LED goes off. All right, so that's the job of this part of the code. And then here we have the enable clocks proc subroutine. And then this initialize port F proc subroutine here. And then the initialize UART5 proc subroutine here, all the way, stretches all the way down here. All right. And then we have the configure UART5 proc subroutine. Right, and then the UART5 transmit proc subroutine here. It's here. Then the UART5 receive proc subroutine. And here is the character table that we mentioned earlier. And we finish up with the END directive to signify or indicate the end of the program. So this is the complete listing. The program explanation. Okay, so this part here, as I mentioned earlier, this is the initialization part. And here are the declaration of the registers that are used in this program. As I mentioned previously, I have covered these in my previous videos. So if you're new to the channel and you would like to have more information, please refer to my previous videos. I've included the links to those videos in the description. Okay, let's come back to this. Now, these two symbolic names has been assigned these hex values. These are the control registers, and these are the UART5 registers. All right, and then these are the GPIO registers for port E. All right, for port E, and these are the GPIO registers for port F. Okay, so here is the main proc routine, and let's start out with these 4 instructions here. These are 4 BL instructions. BL stands for branch with link. Now, each BL instruction will call or invoke a subroutine. So, for example, BL enable clocks. This instruction here will call this subroutine, which will enable the clock for UART5 module and the GPIO port E and port F. Then followed by the initialize port F subroutine. Then it will call the initialize UART5 subroutine. And then the 4th BL instruction will call the configure UART5 subroutine. Then here we have these 2 instructions. The LDR4 equals char table instruction. This will copy or load the address of the char table into register 4. Now the char table is a memory location where the string data or data array is stored. So let me just show you the char table, which is at the end, towards the end of the program. Let me just skip the rest and go to that table. So here is the table. All right, here's the char table. Here, array my data, data read only, basically declares a read-only data section named my data. Now you don't have to call this my data. You can call it any other name by any other name. So, and then here DCB basically defines the string which says press 1 for LED on and 0 for LED off. Now 0D hexa is carriage return, 0A hexa is line feed. The 0 here signifies the null terminator, marking the end of this string. All right, so basically this is the char table. So now let's go back to the main prog routine. Next, we've come to the scan input part of the code. And here, this part of the code will scan or read the keyboard. All right. So if the numeric 1 key, all right, so here this part will check for the numeric 1 key. If the numeric 1 key is not pressed, it will branch to this part here, check for 0. Now we'll come back to this in a few moments. Now, if the numeric 1 key is pressed, then these 3 instructions here, LDR, MOV, STR, will turn on the green LED. Now, you don't have to use the green LED. If you want to use the red LED, then you need to use 02 instead of 08. So you need to change this to 02 hexa if you want to use the red LED. Now, if you want to use the blue LED, then you need to change the value to 04. So you need to change this to 04 if you want to use the blue LED. Now let's check out this part of the code. So this part of the code will check for the numeric 0 key. So up here, as I mentioned earlier, if the numeric 1 key is not pressed, then this part will be executed. All right. So here, if the numeric 0 key is pressed, then it will turn off the LED. Here we have 08 to turn on the green LED. Here 00 will turn off the LED. It will be the same for the blue LED and the red LED. 00 will turn any of the LED off. Now, if the numeric 0 key is not pressed, then it will repeat the scan. All right. So this process gets repeated. And finally, ENDP here marks the end of the routine. Now, this is the enable clocks prog subroutine. Now, the purpose of this subroutine is to enable the clocks for the UART5 module and the GPIO port E and port F. Now these instructions here, these 4 instructions here, will enable the clock to the UART5 module, and these 4 instructions here will enable the clock to the GPIO port E and port F. And this instruction here basically is returned from subroutine that would branch back to the main routine. and ENDP here marks the end of this proc subroutine. Here is the, let me just get my pointer out. Yeah, okay. So here is the initialize port F proc subroutine. Now the details of all these instructions here can be found in my previous video, and if you want to know the details, if you're new to the channel and you're not familiar with these instructions, please refer to my previous videos. I've included the links to those videos in the description. So let's get back to these instructions here. Very briefly, these three instructions here will initialize the GPIO alternate function select register, and then these three instructions here will enable the digital function register, and then the next three instructions, these three here, the LDR, MOV, STR, these three instructions will set the direction register as output. And then this BXLR will return the control back to the main proc subroutine, and ENDP here marks the end of this proc subroutine. Now, here is the initialize UART 5 proc subroutine. Now, these instructions here, these three instructions here, disable the UART 5 module. And then these instructions here, these three instructions here, set the baud rate or set the integer part of the baud rate for 9,600. And these next three instructions here also set the baud rate, but this time the fractional part of the 9,600 baud rate. And then here, these three instructions here select the system clock. Now, in my previous videos, I have not explained the integer and fractional part of the baud rate. So let me take this opportunity to explain the integer and fractional part of the baud rate. Now, the baud rate divisor is calculated using this formula. So it's baud rate divisor, or BRD, equals system clock divided by 16 multiply the baud rate. Now, for a baud rate of 9,600, and assuming a 16 megahertz clock, the BRD would be 16 megahertz, 16 million divided by 16 multiplied by 9,600. That gives us 104.1667. Now, the integer part would be the 104 is here, and the fractional part would be the 0.1667. And here we have these three instructions that will set the data length. So in this case, it's 8 bits, no parity, no first in, first out, or no FIFO. Then the next three instructions here enable the UART5 module. And then BXLR here will return the control back to the main proc routine, and ENDP marks the end of the initialize the UART proc subroutine. So here is the configure UART5 proc subroutine. Now these three instructions here, these four instructions here basically is set PE4, that is port E bit 4, and PE5, that is port E bit 5, as digital outputs. And then the next four instructions here, notice the instructions are identical, But these 4 instructions here enable the alternate function or alternate functionality for PE4 and PE5. And these 3 instructions here disable the analog functionalities. And then the next 3 instructions here, LDR, LDR, STR, these instructions here configure configure PE4 and PE5 for UART functionality. And then here the BXLR returns the control back to the main proc routine. And ENDP here signifies the end of this configure UART 5 proc subroutine. Okay, so this is the UART 5 transmit proc subroutine, and basically this subroutine here, this whole subroutine here, transmits a character using the UART 5 module. The wait for TXMT label here marks the start of the loop that checks if the TX buffer is ready for new data. All right, so the purpose of this loop is to ensure that the transmit buffer is ready before sending new data. And these 2 instructions here, they transmit the character that is in register R0. And BXLR here returns the control back to the main proc routine. And ENDP here marks the end of this UART 5 transmit proc subroutine. Now this is the UART 5 receive proc subroutine, and these instructions basically wait for the received data in the RX buffer. Now wait for RX label here marks the start of this loop. All right, now the purpose of this loop is to ensure that the procedure waits until data is available in the received buffer. All right, and these 2 instructions here, LDR and LDRB, basically read the received data, and BXLR here returns the control back to the main proc routine, and ENDP marks the end of the UART 5 receive proc subroutine. And we've covered this earlier, this character table. And END here marks the end of the entire program. Demonstration. Now this is my hardware setup. I have the Tiva C series board, a mini breadboard, some male to female jumpers, the USB TTL adapter cable, and a USB logic analyzer. The connections, so PE5 on the board, following the green jumper wire to the mini breadboard, and then from here it's connected to the receive part of the USB TTL adapter cable, and then PE4 on the board here, which is to receive the RX, that is connected to the TX portion or TX of the USB TTL adapter cable. And then not forgetting the ground of the board that is connected to ground of the USB TTL cable. And then the for this demonstration, the PE5, which is transmit part of the board, is also connected to D0 channel of the logic analyzer. And D1 of the logic analyzer, that is connected to the receive signal of the board, or PE4. And then the ground must be connected to the logic analyzer. And lastly, not forgetting the USB connector that needs to be connected to the laptop or your desktop. And then in addition to the hardware setup, you would need the TerraTerm terminal emulator. All right, so we need this software. Okay, so here is the Kyle Microvision IDE. I've uploaded the code here. So let me just briefly go through the code. So here is the initialization part. This is the declaration of all the registers and relevant addresses. Here is the beginning of the main proc routine, ends here, and then here we have the enable clocks proc subroutine, followed by the initialize port F proc subroutine, and then we have the initialize UART5 proc subroutine, which stretches all the way down to this part here. And then we have the configure UART5 proc subroutine. Then we have the UART transmit proc subroutine, and followed by the UART5 receive proc subroutine, and then finally the char table or the character array, and then the end directive that signifies the end of the entire program. So this is the program. Let me just go to project and do a build target, and we have 0 errors and 0 warning, and then we download the code to the board. All right, so let me just minimize the IDE, place it side by side with the camera. So let me just download the code. Okay, before I download the code, let me just also show you, this is my setup. All right, now we download the code to the board, and it says programming done. All right, let me move it. It says here programming done, verify, okay. Let's go to the actual demonstration. Okay, for this demonstration, I have set up 2 cameras. One camera is looking at the board, the TM4C123G LaunchPad board, and this green LED is the power LED to indicate that the board is power on. Now the LED that I'm interested in controlling is located around this region. All right, so pay attention to this region. Then the second camera is looking at my keyboard of my laptop. Now, the idea is we will have, if I press 1, the green LED on the board will light up. And then if I press 0, it will switch it off. Now, before I do that, this one here is the terminal emulator. All right, so it's displaying the message. Press 1 for LED on and 0 for LED off. All right, so let me proceed with pressing the 1. All right, watch the LED. It's on. The green LED is switched on. Now if I press 0, it switches it off. It turns it off. Now let me do it again. So 1, the LED turns on. 0, turns it off. One more time. 1 is on. 0, it switches it off. Okay, so here is the output of the logic analyzer. I've set it up and captured the output of the Tiva C series LaunchPad board. This is the output protocol for the decoder for the message. So you can see the characters for the message. So it's PRESS for press, space 1 for FOR, space LED, space on. So if I just zoom in a little bit, let's take a quick look at the P. You have the start bit, stop bit, and the binary output for the ASCII uppercase P. All right, so let me just zoom out a bit. Show you the output, or the input rather, of the key press. So here, let me just get myself. So this is the 1 from the keyboard. Start bit, stop bit. So this is the ASCII 1, and this is the binary. So let me just zoom out a bit. Let's look at the other one. Should be the 0. Yeah, so is your start bit and stop bit and the ASCII 0 from the keyboard. Okay, so that's it for this video. I hope you have found it useful, and thank you for watching. I'll see you in the next video. Bye.